Okay, lesson 23. We're talking about the Baeyer-Villiger oxidation reaction. And what this essentially does is we could take a ketone or aldehyde along with the conjugate base of a peroxy acid and yield either an ester or the carboxylic acid. So, here's how this works, is that the negative charge on that oxygen right there will come in and attack here. Again, it's the most electrophilic site that we have here. And this again could be an aldehyde or a ketone, either one. And then we get this crazy intermediate. Okay, so here's what's happening. The electrons from the oxygen fall back down, which means that there would be too many bonds on this carbon. So instead of the normal types of things happening, what actually happens is that one of these R groups, either this side or this side, decides that it's going to shift down and grab that oxygen, which would give it too many bonds, which is why this bond then breaks. So it's kind of like boom, boom, boom. All that sort of happens at the same time. Now, that will give you, in this case, a carboxylic acid. Of course, you can get an ester in other ways, as well as the carboxylate that you would have there as well. Now, the big question here is, how do you decide whether or not this side or this side is the one that comes down and grabs that oxygen? Because that's going to essentially determine which direction your ester goes, or your, in this case, it's carboxylic acid, but in other ones it's going to be an ester. Well, it's actually pretty simple. Hydrogen is going to be first. The reason why is because hydrogen is so small, it just migrates very, very quickly. But beyond that, you basically have the most stable of these. If it were to have like a positive charge or a charge buildup on it, that's the one that will migrate the easiest. So tertiary, secondary was about the same as a phenyl. That has to do with some spatial concerns there as well. Primary and then a methyl would be like the absolute worst thing to actually move. So that's a pretty straightforward reaction there. Sorry, my texting is going off here. Next we have a Wittig reaction. Not a Wittig, but a Wittig reaction. And what this guy is he's a real interesting character. We add aldehyde ketone, usually ketone, but you can do aldehyde as well, I think. And you make what's known as an ylide. We start off with triphenylphosphine is what this sort of looks like right here. And in this case, I'm just doing an example with this particular carbon and making this guy. Now, this is sort of in equilibrium with what we call an ylide. And the ylide, what that means is that, okay, we could have electrons migrate over here, and that's sort of what its conjugate form would look like. So a positive charge on the phosphorus, a negative charge on the carbon, and that would be what's known as an ylide because that has two adjacent carbon or two adjacent atoms with opposite charges right next to each other. And so anyway, this reaction, along with this guy, gives you this new type of alkene bond. So here's what we do to actually make this thing. First, we have to make the ylide. And we do that by adding triphenylphosphine to an alkyl halide of any sort that we want. So in this case, we're actually going to use just basically 3 carbons and a bromine. Notice that this guy comes in here and displaces the bromine. So there's a new connection between this carbon and that phosphorus. You then add what's known as N-butyllithium. Well, N-butyllithium is a mega strong base. And this stuff is so mega strong that if you were to allow it to be exposed to air, it catches on fire like that. It's actually pretty dangerous stuff. So you have to be really careful as to how you work with this. It's very reactive with water, blah, blah, blah. Blah, blah, blah is a lot of danger, so you gotta be careful what you're doing, really. These electrons will come and grab the hydrogen on that carbon, which pulls it down to that phosphorus. And so this is what you end up with, which again is going to leave a very partial negative charge there and a very partial positive charge here, if not actually formally negative and formally positive. So, and you can draw this using the ylide instead of the double bond, that's totally fine. But if you have sort of like a charge buildup on that phosphorus, that means that the electrons from this carbonyl group will come and grab that phosphorus And then the double bond sort of comes back over here. Or you can consider it the negative charge from your illet, if you want to consider it that way. And then, to me, this kind of looks like the 70s dance where you're doing the hustle, right? And you're kind of going, whoom, like that at the same time. All of a sudden, these electrons come up here and these come down at the same time. And that's what ends up giving you your double bond right here. We already have one single bond, because that's what happened here. And then when we move these electrons down, that's what makes the double bond. You also get your phosphorus derivative right there. This does make both E and Z products, so that's something to be aware of. Okay, thank you.